Good morning and welcome everyone to the second day of the Precision Agriculture webinar. I am Dr. Ali Nafchi, Assistant Professor and Precision Agriculture Extension Specialist here at Southwest State University. Today we are privileged to have a panel of distinguished speakers. Our first speaker is Dr. Todd Trooien, Natural Resource Engineer and Professor of Agriculture and Biosystem Engineering at SDSU. Dr. Trooien loves to work with the students here at SDSU by teaching few different courses. His research focuses on irrigation, especially subsurface irrigation, drip irrigation, and animal wastewater used for crop production. Dr. Trooien will be discussing subsurface drip irrigation, a great technology for placing water directly into the crop root zone and at the precise time when the crop can use it. Thank you for being here. Let's begin with our first speaker, Dr. Trooien. Over to you, Dr. Trooien.
Hey, great. Thank you so much, Ali. It's great to be here on a bright January day coming to you from the Raven Precision Ag Center here on campus. Wonderful new facility we've got here. So I'll talk about subsurface drip irrigation and kind of in general for a while, and then we'll apply the animal effluent application part to that. So that's how we'll go through this here for the next few minutes. So let's start with SDI, or subsurface drip irrigation. And we'll start with the negative example, right? What it's not. And it's not surface drip, right? So here you can see a couple of drip lines in a berry crop on, this is actually on Long Island, New York from many years ago. So this is not what we're going to talk about today, right? This requires some additional labor to pick up and lay out drip lines, and is important for many crops, but generally not for commodity field crops in the Midwest of the U.S. Similarly, we're not talking about the standard grape irrigation system where we actually hang a drip line on the trellis, right? So what are we talking about? We're talking about permanently placed tubes, right? Plastic tubes. Permanent being we plan on a system life of 20 or 30 years for the system, and relatively thick-walled plastic, even though it comes in rolls as a tape. And then we bury that then at a constant depth in our field. And we can have different depths of 10 to 18 inches depending on preferences. Depending on site characteristics, depending on planned cropping characteristics, and we have some flexibility in the actual depth of those drip lines, and then we're going to place those drip lines at a constant spacing. Historically, we would see a lot of 60-inch spacings, and that works really nice then with 30-inch crop rows. More and more now we're seeing narrower drip line spacings down to 40 or even 30-inch spacing. So we're adding a lot more drip lines to that field. And then along those drip lines, then we have emitters, discrete places then where water exits the tube through an emitter. And we have the emitters then at constant spacing, and we can buy them from the factory at various emitter spacings. And again, we'll match that spacing to our needs and our situation, our soil type, maybe our planned cropping system, and so on. So here's an overview of subsurface drip irrigation. And what it looks like then is here we'd have perhaps 60-inch drip line spacing in 30-inch corn rows, right? So in this situation, then every plant is within 15 inches of a drip line. We have that constant spacing then throughout the field. And those drip lines then are depending on producer preference, 10, 12, or 16, 18 inches, somewhere in that range. a different look at it then from, again, the same kind of spacing configuration where we'd have drip line spacing at twice the crop row spacing. So these are permanently installed and then providing water directly to the crop root zone. Right, so some characteristics here then. We're putting the water directly into the root zone where the crop can use it the best, and we don't have to worry about infiltration problems if we get the water right into the root zone. Placing the water at discrete points from those emitters. We're not wetting the entire surface and hopefully not wetting the surface at all. So we reduce some evaporation from the system and perhaps adjust the humidity of the crop canopy. And then we are relying on the soil to help us move the water from wet areas to dry areas. And we're also relying on the crop roots then to grow toward the drip lines. Here's an image in a really nice productive silt loam soil, and you can see the water movement there. The darker soil indicates wetter soil. You can see how water moves laterally and upward and downward, to be sure, from that drip line. And this drip line is probably buried at a depth of 16 inches below the soil surface. Can't see the soil surface on the image in this case, but it'd be not too far above the top of that image. So you can see how water is moving there in the soil, and we're depending on that movement to distribute the water to the plants. Okay, so why are we doing this? Some of the advantages then of SDI, subsurface drip irrigation. It's probably the most uniform and efficient way that we know right now to apply water, to get water to a crop or to the plants in the field. Right, there, our uniformity down the drip line is very high, can be very high with a properly designed and installed system, and that gives us good control of the water, and in any nutrients we might use might apply with the irrigation system. And certainly any salts then that come with our irrigation water supply, as they always do, and so we can manage those salts and move them out of the way if we need to in an effective way. We can apply small, frequent applications uniformly with the SDI, and so, for example, we can do daily irrigations to just meet the crop needs, right? Each day we can meet that rather than applying a bunch of water and then letting the crop catch up for a few days. These SDI systems are very good at applying nutrients, fertilizers, or animal effluents, and we'll talk in some depth about that later on here, of course. Of course, anything you inject with an SDI system has to be water soluble. So any fertilizer that you might want to inject it with an SDI system, got to make sure it's water soluble, or you'll cause problems with those emitters and probably clog emitters, and then that causes problems. Because all the drip lines are buried, we can be doing field operations while we're irrigating. And then a couple other advantages related to physical parts of the system, right? Not nearly as much steel involved, so corrosion, especially where we have corrosive water supplies, we can deal with them. Okay, nothing's perfect, right? So there are some downsides, some drawbacks to SDI. And the first one right up front, it's expensive to install, right? So we've got to get through that high investment cost right away. Having said that, there are folks in South Dakota that are using these systems and really happy and really doing well with them. So there's high cost, but the returns can overcome that investment cost. Secondly, then is the most common reason for loss of micro irrigation systems worldwide, and that's emitter clogging. Right, those emitters control the flow of water out of the system into the soil, and so they tend to have very small flow paths, and we've got to keep them clean. Got to keep silt and sediment out of there. Got to keep bacteria from growing in there and clogging things. So we got to pay attention and prevent clogging, and we'll talk about some specific steps to do that here in a minute. Can't go out and just look and see if there's water coming out of all the sprinklers anymore because the emitters are underground. So we've got to use some indirect indicators, pressure gauges, flow meters, to make sure things are operating properly. Stuff happens to those drip lines, especially the next one. Rodents can be an issue, gophers, ground squirrels. So if they get into the plastic and chew on the plastic, then we got to dig them up and do those repairs, and that takes some work. Finding the leaks generally isn't too hard. You can find them by looking at the soil surface usually, but then you got to dig them up and fix them, and that isn't a whole lot of fun. Mention salts again here. We have to manage those. And sometimes that can be a little complicated if we get into a really dry spell, but we can do that. But we have to realize that we got to make sure we handle those salts one way or another. Okay, that's an overview. Late colleague Freddie Lamb assembled a couple pages of advantages and disadvantages at this URL, so I'll just point you to that if you want to go look at that list for further explanation and further advantages and disadvantages. Okay, let's talk a few minutes about how we install these irrigation systems, just to help us understand them a little better. And the first step then is plowing in the drip lines. And so you can see here we have a two-shank drip plow. It's really just a subsoiler shank with a tube on the back side, the trailing side, to guide the tape from the reels. You can see two reels above the drip plow. Actually, you see three reels. We're just using two of them at the time on this one. And so we'll go through and place those drip lines at depth and at the proper spacing as our first step. Then once all the tape is in, we move away from the mechanized part and we get into a bunch of manual labor. Now we make a trench at the top and the bottom, and we have to expose each of those drip lines and then connect the drip lines then to our water supply system. And we see a couple of different methods of connection there. In the lower right, you can see the PVC supply pipe. This is actually a research location, so we're using relatively small diameter supply pipe. But you see a couple of different ways we make that connection then from the pipe to the drip line. So some serious labor involved here for installation, and certainly that's part of the cost then of part of the investment cost. Okay, again, we mentioned that biggest danger is emitter clogging. And so let's take a look at some of the specific steps that we'll take to prevent that emitter clogging. And we'll use our 5-step program here. So first step in the 5-step program is to select the proper components, especially the emitters, because that's where the action is, where the flow control is, and where the clogging happens if it does. And so we want to choose emitters with the largest flow rate possible, who have bigger flow paths than within reason. And generally, using greater flow emitters can increase the cost of the installation slightly. We need more control hardware and so on. Drip line runs can't be as long. So there's the compromise: select emitters with greater flow rates as great as we can, to make a reasonable system. Okay, so that's step one before you even start installing, selecting the proper hardware. Step two, excuse me. We got to have some level of filtration. Here are some various methods of filtration. There are always some solids in our water supply, so we got to remove them to the extent that we can. If you're pumping groundwater, pumping a little sand into your groundwater, you want to make sure you get a sand separator in there, hydrocyclone in this case, to remove that sand. And then the general filtration, maybe if you got good clean groundwater, some relatively low-tech screen filters might be adequate for you. Step up might be these disc filters, stacks of plastic discs with grooves in them to provide filtration. Or if you got a real challenge, then probably you need some sand media filters, and these are probably the best level of filtration we know how to do right now. They do require some management to make sure that they operate properly. How do you know how much filtration you need? The first step is to find out from your emitter manufacturer what is required to protect your emitters. The emitter manufacturer will say that these emitters require, for example, 80 mesh filtration, or these emitters require, for example, 120 mesh filtration. So that's your first step, and then you can work with your irrigation dealer then to figure out, do you need sand filters, or can discs or screens, or can they be adequate for my situation? Okay, so there's step two, filtration. Number three, then we need some sort of facilities to inject some chemicals to control biological growth. Inside those drip lines is a really nice growth environment, right? Dark and moist, humid in there. And so if bacteria grow enough, they can grow enough to clog emitters. So we want to stop that. So an occasional injection of chlorine bleach, for example, will help with that. Or you can maybe use a different form of chlorine depending on your situation. In this case, we've got actually a couple of injection systems there on the left side. This is injecting animal wastewater here, animal effluent. So this is constantly injecting some acid to control the pH, and constantly injecting some chlorine bleach to provide the biological control within those drip lines, right? And again, work with your dealer to design your injection system to control as much as you need. If you have good clean groundwater, one injection in the fall each year of a good chlorine shock dose might be adequate. One last note, if you are working with acid and chlorine bleach, make sure to keep yourself and others safe by not mixing acid and bleach, right? Because that'll generate chlorine gas, which we don't want to inhale. So be careful out there. Okay, chemical injection for biological growth. Even though we are filtering solids out of our water stream, there's always smaller stuff that gets through. So we need to have some way to flush that out at the bottom end of our irrigation system. So here's a flush valve in a field that's flushing water out of those drip lines, and you can see there's stuff in that water there, a nice brown color, right? And we can generally tie together multiple drip lines at the bottom of the field, so we don't have to flush each line individually, but we can use a manifold then and flush multiple lines at one time. Okay, finally then, the 5-step program, we want to monitor the system to make sure things don't get out of control. And so that means we need to be watching pressures at various locations in the system. And so here's a schematic diagram from the upper right there, your water supply, to the lower left, the actual drip lines in the field. All right, so pressure gauges at various places in the system, especially above and below your filtration system. so that you aren't pushing stuff through the filter. If you have a pressure differential across that filter that's too much, you can actually push stuff through the filter, and we don't want to do that. Pressure gauges at various places in the inlet manifold or the flush manifold in the field. So make sure we don't have leaks or clogs in the field. And then certainly we need flow meters to measure the water that we apply and make sure the flow rates are appropriate. So flow rates, flow meters and pressure gauges to be sure to monitor our system. So there's the 5-step program to keep our emitters flowing like they should. Okay, let's talk about applying effluents here. We haven't got to that. And I'm going to use effluent, excuse me. Sometimes you might hear it called wastewater. I want to call it an effluent because it's a resource rather than a waste product. And we want to think about it as a resource rather than just a waste product. And some sources that might be viable and have been used, feedlot runoff ponds, as you see in that image there, dairy barn effluent, swine lagoon has been a success. Swine lagoon effluent has been applied successfully in SDI. A pit underneath the barn. We're going to actually initiate a new study this spring, applying pumping out of a swine pit into an SDI system. And then certainly treated municipal effluent can be used, and much of, for example, the Mediterranean basin. Many places in the Mediterranean basin using treated municipal effluent as irrigation water supply. Okay, some benefits of doing this. First, saving potable water resources for other purposes, for high value purposes, right? And secondly, then, and certainly very important, is we're recycling those nutrients in the wastewater, right? It's not free fertilizer, but we're not paying any extra for it either, right? And then finally, we can control the application very, very well with SDI. So we should be able to reduce any adverse environmental impacts, such as nutrients in runoff or such as nutrients in our leaching water, right? If we install a properly install a well-designed irrigation system and then manage it well. Okay, and I want to reiterate again, now we're not talking about disposal, but we are talking about efficiently using those resources. And especially then those resources include water, nitrogen, and phosphorus. And we would think about how we would apply the effluent to make most efficient use of these three resources. And generally that means we would apply effluent to fully meet the crop needs of one of these resources, and then supplement with fertilizer or clean irrigation water then to meet the rest of the needs. So for example, it might be an example might be something like this, and you can change the numbers to fit different situations. This is just an example. If we have, if we're going to irrigate a corn crop, and we estimate that crop is going to need 8 inches of water to supplement the rainfall, and the crop is going to need 40 pounds per acre phosphorus, and nitrogen needs are going to be 300 pounds per acre, right, for the full season for that crop. That's what the crop needs. And now our effluent source, we go out and we take a sample and send it to the lab, and they send the results to us, and they tell us that we've got 35 milligrams per liter phosphorus and 120 milligrams per liter nitrogen in that wastewater. So how do we use those resources most efficiently? We see that we do a little math here, right? And so at a phosphorus concentration of 35 milligrams per liter, if we apply 5 inches of effluent, that gives us that 40 pounds per acre of phosphorus. So there's our limiting factor there, that's phosphorus. Those same 5 inches of effluent give us 135 pounds of nitrogen per acre. So we still need to make up the rest of that to get to 300 pounds per acre. So we need to apply 165 pounds per acre nitrogen as fertilizer. And finally, then, if we apply 5 inches of effluent to meet the phosphorus needs, that means we still need another 3 inches of water, of clean irrigation water, to meet the crop water needs. All right. So now we're using all of those resources in the effluent as efficiently as possible. We have to add some fertilizer and some clean water. All right. Recall again, we want to make sure we protect our emitters with the 5-step program. That means we need to have some access to some clean water. We can't use just effluent, but we do need clean water to do some flushing. If we're using clean water, then we have to make sure we protect that water supply, and that might be by using something like check valves and electrical interconnects to make sure that we can't push effluent back into our water supply. And there are multiple places where you can find recommendations for backflow prevention to keep our water supply clean. There we go. Let's wrap it up and take it home. SDI is a good irrigation technology, and we want to make sure we protect the emitters to protect our investment, keep that system running, and we can apply effluents such as animal effluents with SDI systems to reclaim the water and the nutrients in those effluents. With that, I thank you for your time and your attention. Horace was an ancient Greek philosopher. He knew me pretty well, and there's my contact information in the upper left. And Ali, I will turn it back to you at this point.
Thank you very much, Dr. Trooien. We have 2 questions. The first question is, how does drip line handle the freeze here in South Africa?
Yes, so generally what will happen is you will blow out the system at the end of the growing season. So you'll evacuate the system, remove the water. One of the dealers that I get to communicate with a lot says he will generally blow out SDI systems that are north of I-80. If you live south of I-80 going through Nebraska, then it doesn't freeze hard enough during the winter to be a problem. If you live north of that, then you'll want to blow it out in the fall or drain it somehow.
And we have, thank you. We have another question is, how can we detect the leak damage in the drip line when it's under the soil?
Yep, good question. And that's where the pressure gauges and flow meter come in. So if for example, you have a pressure gauge at the inlet of a zone, that is the top end of an irrigation zone, and normally that pressure gauge, you set the system so that the pressure there is 10 psi. If your normal setting results in, for example, 4 psi at that inlet, you know something is wrong. And further, you can go check your flow meter then to make sure that the flow rate is what it's supposed to be, what it's designed to be. If in this example it's a little higher than the design and a low inlet pressure, you probably have a leak somewhere.
Thank you. Thank you.
Thank you.
All right. So we have a poll for this session. Please answer this question. We have a few questions for poll. And that will help us to improve our program. And following to Dr. Trooien presentation, we are transitioning to our second speaker, Dr. John McMaine, Griffith Chair in Agriculture and Water Resources, Associate Professor, Extension State Specialist, Director of Mesonet at SDS State, and Director of South Dakota Water Resources Institute. Dr. McMaine is passionate about solving challenges related to the water and weather in South Dakota and across the northern Great Plains. Dr. McMaine talks about precision drainage system today, an advanced agriculture drainage technology designed to optimize water management in fields. This approach improves water removal efficiency, reduce soil erosion, and enhance crop yields by maintaining optimal soil moisture level. Let's begin with our second speaker, Dr. McMaine. Over to you, Dr. McMaine.
Wonderful. Thank you so much, Ali. And I will get the presentation going. All right. Well, thanks for joining us this morning. And as Ali said, I will be talking about drainage primarily today, and specifically get into automated controlled drainage. But before I get into that, I want to go through some stuff that I really think helps us understand why thinking about drainage or why thinking about water management is really important, especially in South Dakota and really anywhere along the 100th meridian. And so that's kind of as we transition from the eastern U.S. to the western U.S. And it's important beyond there, but we have a particular set of challenges that we deal with. And I think the main challenge is that we never get the appropriate amount of water, right? You either get not enough, as you see in the top picture, or you get too much, as you see in the bottom picture. Both of these pictures were taken pretty soon after I started at South Dakota State, so within the first probably 2 or 3 years, and it really drove home to me this challenge that farmers especially, but also municipalities, homeowners, there's always the potential that the weather could swing one way or another, and you end up getting way too much or not enough. And if you've ever seen any presentations from my colleague, Laura Edwards, the state climatologist in South Dakota, one of the things that she talks about is really the challenges of these are becoming more extreme. So you have longer and more intense dry periods, and then more intense precipitation events, which leads to the type of picture that you see on the bottom. And so another way to think about this is with crop insurance claims. And I want to start with 2019, not because it's the most recent, but because it was probably one of the biggest challenging years that South Dakota and Nebraska and Iowa had in recent times, and that was because of excess moisture. So if you remember back to 2019, we had a wet fall in 2018, so the soils were saturated, they were frozen, and so then you had a lot of this, and then we had a bomb cyclone event, so a lot of precipitation, a lot of rainfall in spring of 2019, and all of that rainfall fell on soil that really couldn't take it in. And so we see this too in South Dakota and in the northern Great Plains. We have these rain on snow events or rain on saturated soil events, and that makes managing water really challenging. So thinking about kind of the macroeconomic scale for South Dakota, looking at crop insurance claims, over 60% of the crop insurance claims in South Dakota in 2019 were due to excess moisture, and that's really not a surprise. But the interesting thing is, if you look at a lot of other years, we see that trend is something it's been changing the amount of precipitation we get, And if you look at these two time periods from 1961 and 1990 compared to 1991 and 2009, if you compare those two, that's what this map is showing here. And on the really, really dark is more than 5 inches of annual precipitation in that more each year in that second time period compared to that first time period. But then, anywhere from 1 to 4 is what we're seeing in eastern South Dakota, eastern North Dakota, and western Minnesota. So what you have is a landscape that's maybe adapted to, or farming practices that have adapted to maybe a little bit drier conditions. And then in the last probably 30 years or so compared to the previous 30 years, we've seen a pretty dramatic increase in precipitation. And all that water has to go somewhere. Like something has to be done with that water to productively grow a crop. And it's not just the amount that has changed, but it's also the timing. This is from that same work done by colleagues, Dr. Chris Hay, Dr. Dennis Toddy, who were previously at SDSU. And we see again, this is for fall precipitation. And in this eastern South Dakota, eastern North Dakota, and a little bit into the central part of South and North Dakota, we see an increase in fall precipitation as well as an increase in winter precipitation. And the challenge, especially with fall and winter precipitation, is that has no chance of going back to the atmosphere as evaporation or as transpiration, the amount of water that plants use. And so really it's just going to sit, and that's going to lead to wetter springs, which is what happened in 2018 or 2019, excuse me. So we know, or those slides show us that things have been wetter. But if you look at the last couple of years, we also see that we've had some pretty intense dry spells. And so the other interesting thing to think about is having both of those challenges within the same time period. So this is crop insurance claims from 2018. And the number one cause for crop insurance claims in 2018 was excess moisture, with almost 35% of the crop insurance claims. But then number two is drought at almost 20%. So you have the opposite ends of the spectrum in the same state and the same year. You have both too much water and not enough water that's leading the crop loss in South Dakota. And 2017, it's flipped. But again, the number one and number two leading causes for crop insurance claims are at two opposite ends of the spectrum. Not enough water and drought, and excess moisture is number two. And so, I realize that South Dakota is a big state. We have this precipitation gradient where it's wetter on the eastern side of the state, drier on the western side of the state. So maybe it's just due to that you have differences across the state. And so we wanted to dive a little deeper and say, how localized is this phenomenon? And so what we found at 4 counties kind of along the I-29 corridor, starting up in Cottington County, which would be Watertown, Brookings County, which is Brookings, obviously, Minnehaha County, Sioux Falls, and Clay County down around Beersford. So along this I-29 corridor, and if you look, I'll just turn on the laser pointer here. So corn is the top one here, and then soybeans is the bottom one. And so what we did is we looked at in each county in each year for the last 30 years. So that's 30 years, 4 counties, that's 120 county years. Then how many or how often did the same county, the same year experience both excess moisture and drought? How often did it experience only excess moisture, and how often did it experience only drought? So if you go over here to the right to the totals, 89 of those 120 county years had both excess moisture and drought in the same county in the same year for corn. Now for soybeans, it was even more. So for soybeans, out of those 120 county years, 100 of those had crop insurance claims due to both excess moisture and drought in the same county in the same year. So clearly this creates a significant challenge. It's not just that we're getting rid of excess water, but we also we need water in the summertime. So it's a nuisance in the spring, and it's a resource in the summer. So how do we manage that? How can we handle that? Well, one of the ways that South Dakota farmers have looked to manage water is to tile drainage. And so this is a study from Iowa State University. I just want to quickly walk you through what we see here. On the x-axis, this is the year. On the y-axis, this is the yield. Don't worry about kilograms per hectare. I know those are units that we're not, we don't normally think in. We usually think of bushels per acre. But let's just compare the differences. And so the all black is shallow tile. The gray, light gray is conventional tile. The darker gray is controlled drainage, which we'll talk about more. And then this diagonal line is no drainage. And then these letters above each bar, they represent statistical differences. And so even if you have numerical differences due to randomness and variability, we run statistics on this data. And if there's a difference in the letter, that means that the different treatments are actually different, statistically different. So in 2007, there was no difference among all of our different tile drainage treatments, including, even though numerically it was lower, there was no statistical difference with no drainage compared to the other three. Same for 2008. There's no difference amongst all the tile drainage, even though numerically no drainage was higher. So no statistical difference. 2010, again, no statistical difference. 2009 is the only one that we actually saw a statistical difference where no drainage had a lower yield, but it was only different to the shallow tile and the conventional tile, not to the controlled drainage. So then that might lead you to say, well, how much difference does it actually make year in and year out? And if you take the average, we do see that on average, the no drainage did have a slightly lower yield, statistically different, numerically not a lot of difference, but it did have a difference in drainage, or in yield, excuse me. And so we can say from this study, this study doesn't represent all fields and all precipitation patterns, but in this study, tile drainage on average increased the yield compared to no tile drainage. But if we look at the variability, we see that really only occurred in this 1 year. So maybe that's something to think about, at a big picture scale, at our field scale. Does it make sense to tile the whole field, especially in situations where, again, not statistically different, but numerically, we actually had a higher yield with no drainage. There may be some years that no drainage may do better. And we think about that, there's wet spots of the field, but in dry years, those do really well. If we drain those, well, then we take away our advantage in dry years. And so that's maybe the first step to thinking about precision drainage or precision water management from a drainage perspective, is not draining, like only draining what is going to give us the best bang for our buck over a longer period of time. And we can do that through thinking about what parts of the field actually need it on a consistent basis. After 2019, I talked to some farmers that the number one thing they wanted to do was they wanted to go in and they wanted to drain every part of their field, every part of every field. But then, when we had a conversation, turns out that not every part of every field had a consistent issue. It was only that 1 year that was really bad. And so, it's a big investment to put in tile. It may not make sense to do that for every part of every field if it's only an issue, maybe 1 out of 5 years, 1 out of 10 years, something like that. So that's the start to think about tile drainage. But then let's think about how can we use tile drainage and other tools to maybe hold on to that resource or use that resource in the future. So what this graph shows, and I'll use the laser pointer again, on the x-axis we have the months of the year, so January through December, And on the y-axis, we have precipitation, or the amount of water that comes down from the atmosphere, comes down from the sky, and ET, or evapotranspiration, which is the amount of water that goes back to the atmosphere. And so for most of the year, the precipitation, the amount of water that comes down, is higher than the amount of water that goes back up. And so really that's when we see the most benefit of our drainage. But then in this middle part, we see a big benefit, or we see a big need for more water, for ET. This would be where we see our most irrigation potential, like Todd was talking about, or what we're going to talk about in a second, controlled drainage. So one opportunity to hold on to that water is something called controlled drainage, or drainage water management. Now, how controlled drainage works is essentially you have these structures in the field that are along usually a tile main. And within this structure, there's different stop logs that you can add at different levels. And so basically, with those stop logs, they act like a check dam within the field. And so if you put 3 stop logs in here, then the water will have to get to that level before it leaves the field. So essentially, you're managing your water table depth at whatever level you set your stop logs to. And the benefit of this is you can take all the stop logs out, and this behaves just like a normal conventional tile drainage. And then you still have control, though, if you hit June or you hit July and you're starting to get really dried out, well, you can throw a couple stop logs in there that are going to hold on to any of those timely rains that you may get. Now, I want to just go through this quickly to talk about how much water we could actually save. So this is from a modeling study that we did just to look at opportunities for controlled drainage. And I won't get into too many of the details, but basically we modeled the drainage, the amount of water that's coming off of a field from 1950 to 2012. And from that, we looked at if we had different control boards within that control structure, how much water could we have actually saved? And so that's the years is on the x-axis. The y-axis is the depth of water saved in inches. And so some of these years, if we think about saving a ½ inch or more, several of these years we were able to save a ½ inch or more. Several of the years we were able to save an inch or more. How many years? Well, in 20 plus of those about 60 years, we were able to save a ½ inch or more of water. And in 13 years of those 60 plus years, we were able to save an inch or more. So 30% of the time we could have held on to a ½ inch or more of water. And in 22% of the time, we could have held on to an extra inch of water. How much difference does a ½ inch or an inch make for a corn crop? Well, if we look at that, and this is a really great figure from Dr. Justin McMaine from University of Nebraska-Lincoln. And what he's diagrammed here is the amount of water that's used per day throughout the growing season. And so if you look at, say, in this peak growth rate, when we're here kind of VT to R1, getting into the reproductive stage here, that's about 1/3 of an inch of water per day. And so an inch could save us in yield, and we have an 8% yield loss per day if that crop is stressed. So that could save us an extra 24% in yield, or 3 days at 8% yield loss per day. If we're in this kind of V10 to V17 or V15 to V17 stage, then we would be closer to a 16% yield loss that we've saved, or 4 days at 4% per day. So an inch of extra water in the soil profile could potentially go a long way. I mean, that's going from, instead of 200 bushel corn, you'd have 212. Basically, if you're looking at 24% yield difference there. So how many, this is just a comparison between controlled drainage and free drainage. And sorry to be showing you lots of figures, but I want to drive home the point that, this can have a lot of value. And so what this is on the x-axis, this is a study that looked at 8 different states, controlled drainage compared to free drainage. And across the x-axis, we have how much precipitation we received during the growing season. And so if it's greater than 1, it means it's wetter than average. If it's less than 1, it means it's drier than average. If it's greater than 1 on the y-axis, it means controlled drainage did better than free drainage. If it's lower than 1, then free drainage, just the traditional no stop logs, did better than the controlled drainage. What you see is there's a lot of dots in this quadrant number 2, which means when it's drier than average, controlled drainage typically did better. You also see a lot of dots in this quadrant number 4, which means if it's wetter than average, then the free drainage actually did better. And that comes down to a management issue. And so essentially what we have is an opportunity after planting, but we also have to be careful that we don't manage that water too high to the surface. Otherwise, we lose the benefit of the drainage, and we could actually hurt our yield that way. We also have an opportunity after harvest. So we can put those stop logs back in after harvest. And this is primarily going to help us from a water quality perspective. Any water that leaves the field also potentially has nutrients that are leaving the field. So if we can keep the water in the field, that also means we keep the nutrients in the field, which means less goes downstream to cause negative consequences downstream. How does it perform? So controlled drainage as a whole can have a pretty significant nitrate load reduction, anywhere between 20% to about 80%. And the primary reason for that is you can imagine a really wet year, a lot more is going to leave the field, so you're not going to reduce as much. In a really dry year, you're going to be able to hold a lot more of that back. From a yield perspective, we see all over the map. And a lot of this comes down to management, but potentially you could have a really significant increase up to about 20%. In most cases, or in many cases, had no effect. And in one, this is from this study here, in one case, they actually saw reduced yield. And again, that's if you manage that water table too high to the ground surface. So I've said that management really drives the kind of the second challenge for controlled drainage. So how do we get better management? Well, if we, instead of having manual structures that you just drop the boards in, maybe go out 2 times a year and change the height of the boards, we actually now have commercially available, I shouldn't say we, but on the market commercially available is automated controlled drainage, or something that you can program that does it automatically. It changes that water table automatically. It is not to promote one company over the other, but just to let you know kind of what we're working with. We're using the structures from AgriDrain, and I'll talk a little bit more about those in a second. But basically the way those work is you program in thresholds or rules that you're comfortable with, and then when the water table depth exceeds those thresholds, then it lets water go. Some of the benefits or some of the reasons how to manage these is that it's all remotely managed. So you have a cell modem attached to the unit. You have battery and solar panels, so you don't need to run any external power out there. And then you program in 3 parameters. You program in the depth of the water table below the ground surface, the duration that that water table exceeds the threshold, and then how long you want that drain to be open to get rid of that excess water. So just an example, and so if, for example, we were just after planting, then we may not care as much how close that water gets to the water table surface. And so in that case, we may have rules that say if our water table depth is 18 inches below the ground surface for 24 hours, then open the drain for 6 hours. 18 inches, not a huge deal. But if it's 12 inches below the ground surface, it's a little bit bigger of a deal. So then maybe we'll want a shorter duration that we're comfortable with, and maybe a longer time to drain that. If it's only 6 inches below the ground surface, then maybe we want, we're less comfortable with that, and we want it to drain longer. And if it's this worst case scenario, if there's a huge event and we have water table depth at the ground surface, we want that to open immediately and stay open for 24 hours to drain that whole system down. So that's essentially how you would think about programming the automated system. And you can do that. You can program it for whatever times of the year you want. It's really, really flexible. And really your goals here is, again, to aim for that Goldilocks amount of water. We know that too much is bad. So if we manage it too high, that's not a good thing. Too little water is bad. So if we manage it, if we just let it all go, that's bad. So we want that Goldilocks amount of water. And really, you know, if you think about it, you're trying to keep those timely rains for future gains. So anything you get after that crop has started to develop in maybe June or July, you want to have the option to hold on to that water that you can use the week or 2 weeks following that. When you hit that, you know, the tasseling or the B10 stage, anytime you're going to start to see crop loss from not enough water, controlled drainage, in particular automated controlled drainage, gives you the ability to hold on to that water. So just to plug a little bit some of the research that we're undertaking here in South Dakota, we did put in 2 of these automated systems this fall. They didn't have any water flowing through the tiles when we put them in, so hopefully get some rain that we can actually do some research on them. But they are online, and those are at the research farm in Beersford. So if you happen to be close to Beersford and can make it to the field day, we'll try to showcase some of those. We do plan to monitor those in 2024 for both water quality, for the amount of water that comes out, and then also look at yield across drained, undrained, or automated controlled drainage, manual controlled drainage, and then free drainage. So that's all I've got. Here's my contact information. Feel free to reach out if you have any questions. And with that, I will turn it back over to you, Dr. Nafchi.
Thank you very much, Dr. McMaine. We have CCA credit, I think is appear on the screen. You can scan this and apply for CCA credit. And shortly we will have polls. Please answer those questions, and we'll see if we have some questions. So if there is no question, again, I thank you everyone for being here and attending this webinar. Thanks to our speakers, Dr. Trooien and Dr. McMaine. Have a great day.